So now that we've reviewed atoms and our isotopes from before, we can dive into nuclear chemistry. The first thing we're going to talk about is radioactive decay. Radioactive decay is the process where the nucleus of an unstable atom spontaneously disintegrates, releasing two things, energy and matter. So it releases energy, which we can feel or we can sense, but then it also releases matter. So some particle gets released for the ones that we're going to talk about. The first documented observation of this happened way back in 1896. Henry Becquerel noticed that a uranium sample left an image on photographic film. So we know things that are radioactive to be very dangerous, right? We don't touch them, we don't walk around them, we have fancy suits for stuff like that. Back about 100 years ago, people did not know that radioactive material was dangerous to them. So to have a uranium sample just sitting on your desk wasn't weird. And this is the photographic film. You can see that it left like 2 marks from chunks of uranium that they had on there. So this led to tons more research once they noticed this, and they talked more and more about how atoms decay and why it's useful to us, and 2 awesome things were invented among millions of other things, but X-ray machines that we use and nuclear power. So the first radioactive decay we're going to talk about is alpha decay. There's 3 types, alpha, beta, and gamma. So alpha decay is the most common, and in this process, a helium nucleus is emitted. So remember we said it emits matter and energy. The matter that's emitted in an alpha decay is a helium nucleus. Now notice that we say it's a helium nucleus. It's not a whole atom, so it doesn't have any electrons on here. It's just the middle part. So remember, helium has 2 protons. Let's make those the blue ones. Okay, so 2 of these, and then also 2 neutrons. So everything in the middle of a helium. Now because of that, we start with something, we end up with this alpha decay particle that goes shooting off into the distance, and we get this new atom here, this new daughter atom is what we call it. So since these 2 protons and neutrons are emitted, we get a brand new element, right? This thing right here changes what element we have. And this thing right here changes the number of neutrons we have, which changes our mass number, which remember is protons and neutrons put together. So to find your new element, it's easy. You just subtract the 2 protons. So if we were on the periodic table and you started with something that had 80 protons, after alpha decay, it would only have 78. And then to find the new mass number, you do the same thing, but we're going to subtract 4 this time. 2 protons and 2 neutrons to come up with the new mass, and then you can use that to find the total number of neutrons. So here's your general equation. You start with something. Remember, these 2 numbers here are very important. This is your mass number, protons and neutrons, and this is your number of protons. So you subtract 4, you subtract 2, just like we said, and those 4 and 2 go into your helium nucleus that's spit off. So curium's abbreviation is CM. This is for Marie Curie. She has 96 protons, so remember that goes down here, and we know her mass number is 248. So after alpha decay, we know one of the things we're going to get out. I always like to write that one first, because we know we're getting out helium no matter what. And then we just got to make sure all these things add up, just like balancing an equation. So if we took 4 from our mass number here, this needs to go down to 244. And then we took 2 protons, so this needs to be 94. Now remember, changing the number of protons changes the element. So now we have whatever element 94 is, which is plutonium. Pu is the abbreviation. So I want you guys to try this one right here on your own. You should have gotten this. So you start with radon. You know you're going to end up with your helium, and then it goes, or radium, sorry, and then it goes from 88 to 86. So you got to find that on your periodic table, and 86 is radon. All right, switching to beta decay. Beta decay is a little weird because In this beta decay, the parent atom emits an electron from the nucleus. So remember, in our atom, we have protons and neutrons in here, positive, neutral, and then electrons should be out here, right? In beta decay, remember this is so excited and it spontaneously emits an electron from here. Now, in order to make that happen, a neutron, so one of the guys in the middle here, turns into a proton and an electron, okay? So our neutron in the middle, which has no charge, turns into something that's positively charged plus something that's negatively charged, and those two things cancel each other out. The proton stays in the nucleus because that's where protons go, and the electron's like, oh crap, I'm here and I'm not supposed to be, so it needs to be shot out. That shooting out of the electron is the matter that's released. The electron is ejected from the nucleus. So this equation looks a little different. You start with something, and you end up with this guy here. You end up with an electron being shot out. Your electron has 0 mass, remember, compared to the proton and the neutron. So that's why your mass number will not change. It stays here, and this is 0. But, remember, we're changing one of, this guy right here, we're changing, oh, blue is a terrible color. Let me change it. We're changing this neutron right here into a proton, okay? Same guy here. So what happens is we got to add one to our proton, which again is going to change the element. So let's do beta decay equations. So first we got to do sulfur 35. So we all know sulfur. We got S on here. If we look on the periodic table, it has 16 protons, and it tells us it has a mass of 35. So we're going to undergo beta decay this time. Again, I always like to write what I know is coming first. So an electron is going to be shot out. My electron has no mass, and I'm going to take away a proton. Because remember, we're going to turn a neutron into a proton. So everything's got to cancel out. So then I'm going to end up with the same mass, 35. But this time, remember, because we're changing that, this needs to have one more proton, because a neutron changed to a proton. So then we look at the periodic table, and the guy that has 17 protons is chlorine. So this changes into chlorine. Just like the last one, I want you to try thorium on your own right now. Alright, and this is what you should have gotten. It starts with TH. You end up with your beta decay right here. And then you add 1, so you got to find your, find that on the periodic table, and it turns into protactinum. Alright, last one we got to talk about is gamma decay. So after an atom undergoes alpha or beta decay, the daughter nucleus is in a high energy state. Okay, so the new thing we got out has very, very high energy. Sometimes this excited nucleus can spontaneously emit something else, and what it emits is a gamma ray. Gamma rays are often called photons, so just know that those two words are interchangeable. When it does this, it moves into a lower, more stable energy state. So the whole point of gamma radiation is to become more stable. The weird thing about this is a photon doesn't have mass or charge. So because our mass number is not going to change and our charge isn't going to change, meaning the number of protons doesn't change, the parent atom and the daughter atom are exactly the same, just one's excited and one's not. So in order to show this excitement, we're going to use an asterisk, this guy here, the little star, to indicate that it is very excited and wants to undergo gamma decay. So you'd start with something like this, excited. It undergoes gamma decay, and look, it's no longer excited, but they are exactly the same thing. The photon just shoots off into space. So let's do a gamma decay. This one's pretty easy. So we're going to start with diprosium, so we got to find that on the periodic table. Its symbol is Dy, and it has 66 protons, and our mass number is 152. Remember, it's excited! So it undergoes gamma radiation. Remember 0 and 0 for this. A gamma is kind of like a weird, like fish swimming down, I guess. And remember, it gives us the exact same thing out, except not excited. So, these ones are not difficult to draw your nice little chemical equation. You probably won't have many of these on a test or a quiz. Hint, hint. Try curium right now on your own. Alright, this is what you should have gotten. Don't forget your little excited state, because if it's not excited, this isn't going to happen. So, not only is this stuff useful, it's also very dangerous. Alpha, beta, and gamma particles and rays all pose a risk to us as humans because they all have ionizing radiation, meaning that if you have ionizing radiation, they have the potential to remove electrons, causing something to be positively charged. And the result of this is it can damage something's DNA. And once it damages DNA, you'll learn in biology next year that DNA is kind of like the instructions for a cell. So if you mess up the instructions, you're going to start replicating cells that aren't right. It's like making a copy of like a key. After you do it so many times, that key's not going to fit in the lock and it's not going to serve its purpose. So this damaged DNA can cause the cell to die altogether or just become weird. And when that happens and your cell division is uncontrolled, you get a tumor. If the tumor spreads, then we end up with cancer. So all cancer is just a mutated cell that's decided to grow and grow and grow, and it keeps growing and replicating itself and not allowing healthy cells to grow. And if you've ever known anybody that's gone through chemotherapy, which is radiation therapy, it can actually cause burns to the skin. This is a picture of somebody way back in the day that had burns. They probably had a shirt on or something that looked like this, and then the radiation went through it, and it caused an actual burn to their skin, just like if you touch something hot. So, to stop radiation. Alpha radiation is pretty easy to stop. You just need a piece of paper, and that stops alpha radiation. It's not dangerous to us compared to the other ones. Beta radiation, you need something a little thicker, but like a piece of tin foil, like aluminum foil that your mom uses in the kitchen, that works. Now, gamma rays are the most dangerous, and those you need something like lead to block them. So, make sure you write down any questions you have. We can go over them in class together, and make sure you've answered all the questions. Have a good night.